Okay, guys, can you guys hear me?
Yep.
All right, so let's give it one more minute before we get started. All right, it's a 7:01, so let's get started. Okay, so welcome to our North American Math Competition Knowledge Lecture. So for the guys who are familiar or you came from basically our bootcamp lectures, now like the difference between two series of lectures are very conspicuous. The bootcamp lectures focus a very short going through, right? Basically go through all the important concepts in 10 lectures. While our knowledge lecture can be more granular. We basically give you 8 different sessions, and for each session, we're gonna focus on specific topic. Just try to give you guys as detailed information as possible, so therefore you can take all the knowledge and technologies and try to solve more problems. Another difference is that for our bootcamp lectures, we're gonna focus on a specific math context. For instance, if you want to go for the Euclid, all the problems, or say the majority problems I'll be giving you is pretty much focused on the Euclid. However, for our knowledge lecture, we're going to be more flexible. We're going to see different problems from the Canadian to the American math competitions. I'm also going to give you a bunch of problems from another national math competition like the Chinese, like the European, so on and so forth. Just try to give you guys as much information as possible. So therefore you can use the technology and you can try to broaden your horizon a little bit, try to see different problems and then try to solve different problems. At the end of the day, you will have a feeling that you see, actually all the problems are like so similar. Because for specific concepts, for a specific way how to test all those concepts, different nations use different problems, but the kernel part are exactly the same. You're going to see kind of like similarities from one exam to the other, and some technologies are quite transferable. So that is actually our goal. We just try to give you guys this kind of like a sense. As long as you get a sense, you will see, okay, I see this problem as a deja vu. I might see this problem in another problem in another math competition. So I'll be able to transfer all the technologies from that one all the way to this one. So this is actually where we come from for the entire math lectures. All right, if all good, so let's get started. We're gonna go to our session 4, circle and the coordinate geometry. Okay, so in our session, we're going to split into 2 major parts. One is the circle, the other one is the coordinate geometry. So in the first couple of lectures, we're going to talk about the circle first. Okay, so first thing first, circle I think is actually a very, very important part for the entire geometry. If you guys go to the IMO, you can actually find out actually circle is the most important part for the IMO. If we guys want to make some comparison between that, like the North American team and also the Chinese team, for instance, you're going to find out for the number theory or for the algebra, we guys are pretty much doing similar stuff. So algebra and, for the Chinese team and the North American team, we're almost the same thing. Like the marks are almost the same. However, in order to separate the cream from the double cream, this is actually the circle. You're going to find that the Chinese team actually did way better job compared with our North American team, especially for the circle part. So that is actually the reason why we think circle is the most important and also the most challenging part for the entire geometry. If you guys went to our session 3, in our session 3, we actually focus, let's say session 3, that was actually considered as a prerequisite of the circle session. In that session, we go for the 2D geometry, pretty much focus on the triangle and the quadrilateral or even polygon, so on and so forth. So all the technology we introduced in our previous session will be totally transferable for our circle session. For instance, the most important thing is like the similarity, okay, congruency, and also if two lines, they're parallel to each other, what is the proportional relationship between all the segments? So these are actually considered to be the foundation for all our geometry. So that's the reason why we introduce all those technologies in our session 3. And now we actually basically copy paste everything into our session 4 and try to give you guys as much flowery kind of like elaboration as possible and try to use all those technologies to this kind of the circle related technologies. All right, just kind of like a quick overview where we come from talking about a circle. All right, so with all those kind of like introduction, now we can get started. Today, we're gonna go to our first lecture in our session. We're gonna introduce some basic concepts for the circle and try to use those concepts, try to solve some real problems in our math competition. All right, so the first one, let's go to our session 1. Circle basics. Okay, for the basics, I think for the basic concepts of the circle, this should be quite understandable for most of you guys. So just trying to be more comprehensive for our entire lecture, we want to just try to summarize all those important concepts for the circle. And I'm pretty sure most of these are very familiar for you guys. So if you are familiar with all those concepts, you can just kind of taking this as a quick review, okay? So the first one is the definition. Circle is actually considered like a simple closed shape. So what is a simple closed shape? It's a set of all points in the plane that are at a given distance from a given point, reaches the center, right? It's quite understandable definition for the circle. And talking about the second part, we're going to talk about some basic terminologies. Basic terminologies. So in a circle, let's say I'm going to give you a circle here. So the basic terminologies we're talking about, first of all, let's say from A to B, this is what? This is an arc, right? So this is an arc. Arc can be considered part of the circle, And if this is C and D, I make a connection to C and D. So this is considered a chord, right? A chord. The entire circle, let's say I have a line which is passing the circle, let's say L. The L is considered to be a secant, right? These are basic terminologies. And if my line, let's say from here, just have only one intersection point with the circle, so now I'm going to talk it, this is actually a tangent, right? A tangent. So basically, you can see a tangent is actually a specific case of a secant, right? As the secant is actually moving along the circle from here to here, all the way, these 2 points are degrading into 1 point. So like a secant can be changed into a tangent, right? So secant and the tangent, these are actually essentially the same thing, right? Secant has 2 points, intersection. Tangent have only 1 point. And as long as the tangent is moving from 1 to 2 points, it becomes a secant, and vice versa. And as long as you understand the relationship between the secant and tangent, you'll be understanding that, you see, actually, most of the properties for secant can be transferable into tangent. Later, we're going to see this power of a point, right? In a powerful point, all those kind of like technologies, all those theorems for the secant can actually be transferred into tangent. So these are actually considered the same thing, and tangent is only a specific case of secant. Okay, I think these are quite understandable. Another very important concepts, so the other one is kind of like a sector. Let's say I have a circle and I have two radius. So if I cut the circle into a small portion of it, right? So this is actually considered a sector, right? And another very important concept, maybe I'm gonna give you another graph, is here. This is actually very useful. You're gonna use that from time to time, especially for Euclid. So if you have a angle, they're actually formed by using two radius, and the vertex of the angle actually is the center. So we give this angle a name. This is the central angle. Okay, let's say theta. Okay, the other thing is if I use two chord, okay, and then I find another point, let's say on the circle, I want to do a connection here, I want to do a connection here. Okay, so that being said, your angle are formed by 3 points, and all of them are actually on the circle. So this angle, let's say give a name phi, this is considered inscribed angle, right? Inscribed angle. I think these are basic concepts. And one of the most important things which will be used from time to time is actually phi equals to theta divided by 2, provided they are facing the same chord, right? These are actually something quite simple but important because Euclid tested from year to year. Basically, the central angle and the inscribed angle, as long as they're facing the same chord in the same circle, you know, they have one is twice of the other. So two things you want to make sure. First, they're facing the same chord. Second, they must be in the same circle. Is it right? If you're not facing the same circle, you're not in the same circle, right? So it doesn't make any sense. You want to be in the same circle and facing the same chord. Okay, these are quite understandable stuff. So moving forward, the basics are talking about the area, talking about the circumference. Okay, the area is easy, pi r square, and the circumference is actually 2 pi r. These are so easy stuff, right? And most of the time in our Canadian exams, from time to time, they won't really ask you to determine the area of a full circle. On the contrary, they always give you a portion of the circle. Like we said, this is actually sector, right? The question asks you to determine the area of a sector. So that being said, so let's say this is R. So now, if you want to determine the area or like the total perimeter of a sector, you need to know the theta value, right? This is theta, right? So that being said, if you want to determine the area of the sector is actually equals to pi r square and 330 theta, right? This is actually using one way, or you can use pi r square theta 2 pi. It really depends on how you're gonna use the theta, right? The theta can be 60 degrees, can also be pi over 3. You choose your decision, right? So this is basically the area of a sector. Just a so easy stuff. And also, what about the total perimeter of the sector? This can be written as 180 pi r 2r, something like this, right? I think these are quite understandable stuff. Okay, so these are like the basic terminologies for the circle. And moving forward, let's go to the second part. The second part, we're going to talk about some basic properties of a circle. Okay, we just try to give you guys as much detailed information as possible, trying to be as comprehensive as possible. Important properties in the circle. Okay, what are the very important properties of a circle? The first one is the famous chords of a circle theorem. I think this is also something you are so familiar with. I'm just going to drag it out here. Let's say you got a circle, and in the circle, you have like a chord, AB. Okay, and this is the center of the circle. Okay, so you want to make a perpendicular line through the center to this chord. So the first one says the perpendicular bisector of a chord passes through the center of the circle. Is it right? So that being said, as long as I have a chord AB, I want to do a perpendicular bisector, or we can say the bisection of AB segment, right? So that one is going to pass the center of the circle, which is quite understandable. In the other way, I can also say that if from the center of the circle, I want to make a perpendicular line to this chord, so this line will also be a bisection of this chord, right? I think this is quite understandable stuff, right? As long as you see perpendicular, you'll be able to see this is going to be not only perpendicular, but also bisection. Break these chords into two equal parts. Okay, so this is number one. At the same time, I want to say something also very understandable. In the same circle, the same chord in length. This means they're facing the same arc in length. Also means that same central angle in measurement. Also means same inscribed angle in measurement, right? So this is also, like I said, very important from Euclid's perspective. I'm just going to give you a quick picture. Let's say I have a chord A, B, chord C, D, for instance. Okay, this is A, this is B, C, this is D. This is the center. As long as you have same in the same circle, which is the prerequisite, right? In the same circle, you have two chords, and they're basically the same in measurement. So that being said means what? As long as you have the same chord in measurement, so the two arcs are the same in measurement. One is here, one is here. And also, if we want to construct the central angle, so these two central angles are also the same in measurement. Oops. Can you guys see me? Hello? It looks like my screen freezes.
Your screen is okay, I think.
No, it's actually freezing. Yeah, I don't know, for some reason it's actually freezing. But you can still see me, right? Oh, why it freezes? There's something wrong with my. Okay, I'm gonna stop the sharing for a sec, and then you'll be able to. So I'll re-share it. Maybe something wrong with it. Okay, I'm gonna stop my sharing. I'm gonna restart my sharing. Sometimes it's pretty weird. It just got. Oops. Okay, now we're back. Because previously I was actually already put like all the central angles, and for some reason the central angle doesn't pop up. Okay, so let's continue. So you have two chords that are the same in measurement, aka means you have two arcs in the same in measurement. If you want to construct the two central angles, of course the central angles are also the same in measurement. If you want to construct two inscribed angles, so those two inscribed angles will also be the same in measurement. These are very conspicuous stuff. But trust me, from Euclid into AMC, you're going to use that from time to time. So just want to put you here, help you guys to refresh your memory. All right, so let's continue. Second part, the important theorems in the circle is the angle of a circle theorems. This is actually something we just talked about. Within the same circle, the inscribed angle is actually half of the central angle, right? Just try to give you guys everything in one place. I'm just going to rewrite it here. So if this is theta, if this is phi, phi will be half of the theta. Phi is the inscribed, and theta is the central. Okay, these are quite understandable stuff. Here, one thing I want to give a quick highlight is that in a circle, let's say, if I have a chord, which is not a random chord, it's actually the diameter. Okay, so if you have a diameter A and B, the inscribed circle, which is facing the diameter, this is going to be what? 90 degrees, right? So AB is the diameter. This is actually, it's a necessary and sufficient condition that angle C equals to 90 degrees. Oh, this is also very conspicuous, but trust me, AMC, especially AMC, likes to use it from time to time. Later, you're going to see some real problems. You see, sometimes as long as you see this, like angle C is 90 degree, you should have an automatic conditional react. Okay, AB is actually the diameter, and the midpoint of AB will be the center of the circle. Okay, so let's continue. Here, there's another very important thing in this part. This is the famous, we call it the tangent chord theorem. What is that? It is something like here. Let's say I have a circle and I want to create a tangent. And from the tangent, I want to create a chord, for instance. And then I'm going to give you something like here. Okay, so this is going to be, let's say L. This is A, this is B, this is C. L is the tangent of the circle. And you can automatically have this angle. Let's say this is a theta. I'm going to give a name theta. Theta. This is C. Since theta will be equals to C. This is the famous tangent chord. I think in 1 year in the Euclid, right? I think it's 2009. And in Euclid, the problem, question number 8, B part, the question is using nothing but this tangent chord theorem. Keep using this technology from time to time, right? So the tangent chord theorem saying that, okay, when you have an angle which is inscribed by a tangent and also one of the chord, so this angle will be the same as an inscribed angle which is facing the same chord, right? So they are both facing the same chord AB, right? So as long as you have another inscribed angle facing the same chord, so this angle will be the same in measurement with the previous angle, the one inscribed by using the tangent and that chord. This is a very famous theorem, and people basically use it from time to time. All right. So let's continue. This is the second part. Let's go to the third part. The third part is basically the point and a circle. You're basically talking about some position. Okay, this is quite understandable stuff. Let's say when I have a circle, right? I have a point which is, let's say here, outside the circle. Let's see, I'm gonna put it here. Let's say this is A, this is O, right? If a point is actually outside the circle, OA will be greater than R. This is outside, right? Whenever OA equals to R, means this is on the circle, right? Whenever OA is lesser than R, this is inside the circle. These are quite understandable stuff, okay? But this is actually one thing. I think you guys know this from day one. Actually, in the math competition, sometimes they use another form of this presentation. I think this one is pretty easy. You guys know that from day one. But trust me, in the math competition, they might not use it all the time because they're so conspicuous. On the contrary, in the math competition, they like to use another form, something like here. I still have a circle. I still have a point, which is outside the circle. This time, let's say they're going to make a chord. Let's say this is A, this is B, right? I'm going to put it here, okay? Okay, now I'm going to find another point on the circle. Okay, let's say this is A, this is B, right? This is your point. You want to discuss the relationship with this one, P. But this time you're not talking about OP. However, they find another point on the circle. Let's give a name alpha. So if I want to say P is outside the circle, so actually you can have what? Angle P will be lesser than alpha. Is that right? If P is on the circle, angle P will be equal to alpha. If P is inside the circle, P will be greater than alpha. Of course, the prerequisite is that A and B, right? They must be facing the same chord. They must be facing the same chord, right? You have a chord AB, and from chord AB, you find another point, let's say C, on the circle, then you will be able to create a circle, like an angle ACB. Regardless where you find this angle, regardless where you find this C, I think the angle alpha is always the same, right? Because we talk about as long as you're facing the same chord, the measurement of this inscribed circle will be always the same. C is here, C is here, C is here. It makes no difference, right? So with that kind of prerequisite, we can actually find out the relationship of P point to the circle. If P is outside, so this angle will be lesser than alpha. If P is inside, means they're basically facing the same chord. Of course, P will be equal to alpha, and the same thing applies for something inside a circle. So trust me, this one is actually more useful compared with the previous one when you are in the math competition. Because in the math competition, sometimes you directly find out a line between the circle center all the way to the P might not be so doable, so feasible, let's say this way. You need to do a little bit of work around and try to find out the relationship from the angles perspective. Okay, I think these are quite understandable stuff. Okay, so let's move forward to the fourth part. These are all the very basic stuff, right? So we don't want to give too much elaborations. The next one is the tangent of a circle. So let's say I have a circle. From the circle, of course, from the outside, I want to make two lines, two tangent lines. First is here, second here. This is P. Let's say this is A, this is B, this is my circle center. So first thing first, from a point outside a circle, there are two and only two tangents to the circle, right? You won't be able to create more than two tangents to a circle. Second, AP equals to PB, right? So these two tangents are exactly the same. These are quite understandable stuff. And the third one is from the center of the circle, if we want to make a connection to these two tangent points, then you will find out the radius is actually perpendicular to those two tangents, right? OA is perpendicular to AP, OB is perpendicular to BP. These are actually something quite understandable, but here I want to give you something very important. As long as in the math competition, you see a tangent to a circle, your first conditional react is try to make an auxiliary line from the center of the circle to the tangent points, because automatically you will create what? A right triangle. So this is actually considered to be a conditional react. Conditional react. As long as you see tangent, you want to do circle center connection to tangent point. Okay, this is very important because you will be able to create a right triangle. Okay, and I want to do a quick extension. This is talking about only one circle, right? And you have like a point, create a tangent. As long as you see two circles that are tangent to each other, let's say this is the first circle. Okay, this is the first circle. This is the second circle. Okay, okay. Maybe this is not a good way to write it here, but something just like this. Okay, if you have like the second circle. Okay, so as long as you see two circles, they are tangent to each other. Okay, what is your conditional react? Another conditional react. As long as you see two circles that are tangent to each other, your first conditional react is connect two circle centers. Do a connection. Second is try to find out the common tangent of the two circle. In our case, I think this is the common tangent for the two circle, right? Of course, it has three, right? The other one is actually here, outside. Let me change a different color. But that is not very important for our today's discussion. One is here, one is here. Basically, you have like three in our case. But nevertheless, I think let's focus on this part, the common circle, right? And you're going to find out, let's say O1, O2, this is L. You're going to have O1, O2 reaches perpendicular to L, right? So as long as you do a connection between the two circle centers, and you will find out these, like the segment between these two circle centers is perpendicular to one of this common tangent. Trust me, this looks like so easy, but this actually give you guys an idea how to create the auxiliary line. If you guys familiar with what we introduced in our previous session, we give you guys so many ideas how to create different auxiliary lines, right? For instance, like, as long as you see a bisection plus like bisector plus a parallel line, you automatically have an isosceles triangle, so on and so forth. And this is actually something very important from circle's perspective. As long as you see circle, you see tangent, there are two major ways to put the auxiliary line. One is the upper part. You do a connection between the circle center to the tangent point, then you have a perpendicular line. The second way is you want to do a connection between two circles if they're tangent to each other, and you will find out that the connection between these two circle centers is actually perpendicular to this common tangent. So later, I'm going to show you an AMC problem. You're going to find out as long as you know this, it's like so easy for you to construct all the auxiliary lines and solve the problem in no time. All right? Okay. And pretty much the last part I want to talk about regarding this circle basic concepts is actually you need to remember these two important conclusions. And this because will be used from time to time. Two basic conclusions. Okay, the first one is, as long as you have a circle, I'll give you this line here, it is actually inscribed in a triangle. Okay, this is a triangle, you have an inscribed circle. Let's say this is A, this is B, this is C, and this is like R. Okay, as long as you have this, I think one of the very important thing you need to remember is the area of this triangle will be equals to R times P. What is P? P is actually half of this parameter. Is that right? the area of a triangle can be written as the half perimeter times the radius of the inscribed circle. How to prove that? It's like so easy, because if you want to make some quick auxiliary lines, see, I just want to do a connection. This is A, this is B, this is C. Let's say for this specific green triangle, right? If I want to make a connection, this is R. The green triangle's area can be written as 1/2 times C times R. Is that right? The same thing applies for the other two, let's say the blue one and also the red one. Is that right? So as red, 1/2 C times B times R, right? As blue, 1/2 A times R. So putting them together, the total area is 1/2 times R, A plus B plus C. So we're going to say this part is actually half of this parameter. So the area of a triangle can be written as R times P. This is for one thing, very important. And especially, you see here, this is actually a generic triangle, right? The triangle per se does not have any specific feature. Sometimes if the triangle is a little bit specific, let's say I have a right triangle. Also, I want to create a inscribed circle here. Let's say this is A, this is B, this is C, A, B, C, A, B, C. Do you guys know our original form can actually be simplified a little bit? Actually, R can be written as A plus B minus C divided by 2. Do you guys know this? If you have a right triangle, so the radius of the inscribed circle can be written as A plus B minus C divided by R. Right, just like divided by 2. Okay, this is actually something very important, and actually AMC and Euclid test these two things from time to time. Okay, for the inscribed circle. As you know, as long as you know the inscribed circle, the same thing will apply for the circumscribed circle, right? The circumscribed circle. What about the same thing for a circumscribed circle? Exactly the same thing. When you have a circle, when you have a triangle inscribed, this is pretty much an inscribed triangle for a circle, right? This is A, this is B, this is C, and this is R. Okay, do you know how to determine the area of this triangle fairly quick? Do you guys know this? If I have a circle, and of course I know the circle's radius is R, and again, I'm going to give you this is A, this is B, this is C, right? Can I have a very shortcut way to determine what is the area of this triangle? Yeah, I see Jonathan has the correct answer. S equals to ABC over 4R. ABC over 4R. Yeah, I think pretty much everyone. This is actually so important. Trust me, this is an easy thing, but one of the AMY problem, later I'll show you, as long as you know this, the AMY problem can be solved fairly quick. Okay, this is actually a very important thing you need to remember. Okay, so far, so good. Okay, so this is actually the fourth important concepts. These are, I think, something quite easy, right? We can actually sort it out very quick. And the next one, number 5, we want to talk about a very important thing, which is the cyclic quadrilateral. Okay, previously we talked about as long as we have a triangle, so any kind of triangle, they will be able to find out a circumcircle, right? So there's no exception. As long as you give me a triangle, I should be able to create a circle to make sure all the 3 points are basically on the same circle. However, if I give a quadrilateral or even I give a polygon, this might not be the case all the time, right? If I give you a very weird triangle, yeah, I think that this one is okay. So if I give you something pretty weird, let's say I'm going to give you something, a very strange triangle, a very strange like quadrilateral, it is not really guaranteed that you can have A, B, C, D, 4 vertex on the same circle. Is that right? So that being said, actually, this brings up a very important topic for the circle. As long as you're talking about a circle, you can never get away from this. This is actually talking about the cyclic quadrilateral. What kind of quadrilateral? They can make sure the 4 points are actually in the same circle. And if a circle already has a inscribed quadrilateral, aka this is a cyclic quadrilateral, what kind of flowery properties you can get for this quadrilateral? This is actually something will be tested from time to time for our Canadian and American math competitions. All right, so let's use some time to talk about what are the properties of a cyclic quadrilateral, and at the same time, how to determine a quadrilateral is cyclic. Sorry, these two concepts back and forth, right? All right, so I'm just gonna start a new page. I'm gonna make a line here. The property of a cyclic quadrilateral. Later, I'm gonna say how to tell if a quadrilateral is cyclic, right? Like I said, these are this kind of like a two twin brother concepts. You know one and you should know the other. So let's get started with the first one. What is the property of a cyclic quadrilateral? I think the first thing is actually they will be able to have the 4 vertex have the same distance to a point, which actually the center, right? These are so easy. These are the definition. As long as you have a quadrilateral, cyclic quadrilateral, you should be able to find one point and make sure these 4 vertex have the same distance to this one point. Easy peasy. Second, if a quadrilateral is cyclic, A, B, C, D, then you will be able to find out the opposite 2 angles. They should be complementary to each other, right? Angle D plus angle B equals to 180 degrees, and angle C plus angle A equals to 180 degrees, right? Cyclic quadrilateral, the opposite 2 angles, their sum must be 180 degrees. Number 3, if you have a cyclic quadrilateral, I want to make this 2 diagonals, let's say A, B, C, D, then automatically I should have theta equals to phi, right? Because in the real quadrilateral, you cannot see that, but if I give you the circle outside, you can tell that right away, because theta and phi, they are facing the same chord. Like we mentioned previously, as long as you're facing the same chord, the same arc, the 2 inscribed circle should have be the same measurement. So theta equals to phi, right? If they're facing from the quadrilateral's perspective, if 2 angles, they're actually facing the same length, so they will be able to have the same measurement, provided this quadrilateral is a cyclic quadrilateral. Okay? Then what about number 4? If I have a quadrilateral, it is cyclic, A, B, C, D. If I want to make a connection between these 2 diagonals and they are intersecting at E, then you should have AE times EC equals BE times DE, right? So if you have a cyclic quadrilateral, so those two diagonals, if they intersect at an E point, so the product of one from like two segments from the one diagonal will be the same as the other. Is it right? Number 5, if I have a quadrilateral, they are cyclic, A, B, C, D. Okay, if I want to make an extension from two sides and make sure they're intersecting as P. Okay, if I have a cyclic quadrilateral, if they're the opposite, the two sides, they're not parallel to each other. Sometimes they might be parallel to each other, right? But okay, in that case, I cannot do this. But as long as they're not parallel to each other, I should be able to make an extension for these two sides, and they will be basically intersect at one point, right? Provided they're not parallel to each other, sooner or later they will be intersecting each other. So you're going to have PA times PC equals to PB times PD. This is quite understandable as long as I give you the entire circle, right? The circle goes to here. So that being said, this is actually the secant theorem, right? From power of a point. This is actually the secant theorem from a power of a point. Power of a point actually contains two theorems. This is the first one, right? Power of a point, this is the first one. Two chords, they will basically break into two parts, and the product, they're actually the same. This is the second part. The second part is from outside, you make two secants, but basically you'll be able to find such a relationship. So far, so good? And the last but not least, number 6 is the famous Ptolemy. If I have a circle, if I have a quadrilateral A, B, C, D, right? A, B, C, D is a cyclic. And again, you have two diagonals, then automatically you should have AC times BD equals to AB times DC plus AD times BC. Is that right? So the sum of the product of two opposite sides will be equal to the product of these two diagonals. Is that right? What the crap is that? Okay, so let's continue. The other part is, okay, this is the cyclic. This is the very famous Ptolemy, right? Ptolemy Theorem. Okay? Okay. So here, I want to give you guys actually something a little bit extension. Ptolemy Theorem is actually, everyone knows that. Ptolemy Theorem actually works for the cyclic quadrilateral, right? As long as you're cyclic, you should be able to have such relationship. But what about you do not have a you do not have a cyclic? What if this ABCD just kind of like a random quadrilateral? Do you have something similar to the Ptolemy theorem? Do you have something similar for the Ptolemy? Yeah, I see Kai has the correct answer. That is actually what we call the generic Ptolemy. The generic Ptolemy says, as long as you have an A, B, C, D, this is just like a random quadrilateral, has nothing to do with the cyclic thing, but you're still gonna have what? AB times CD plus AD times BC will be greater or equal to AC times BD. Yeah, and just Kai mentioned, this is gonna be from an equal into an inequality, right? So this is actually the Ptolemy theorem, okay? And we call this is the generic Ptolemy theorem. It means that as long as you have a quadrilateral, what kind of like property it has, just a random quadrilateral, you're still gonna have exactly the same property. However, this equal sign becomes an inequality. Okay, so these are the 6 very important concepts you need to know as long as you're dealing with a cyclic quadrilateral? Okay, I think that answers my first question. As long as you have a cyclic quadrilateral, what kind of properties you're going to have? Let's go to the second question. How to tell if a quadrilateral is actually a cyclic quadrilateral? Trust me, you're going to find out they are pretty much the same thing. Most of the concepts, most of the properties you find out on the left will be used as a determination rule in order to determine this given quadrilateral as a cyclic quadrilateral. First thing first, if, pretty much the same thing, if you can find out for this given quadrilateral, there's a point which has the same distance for the 4 vertex, of course, you'll be able to find out this quadrilateral is going to be a cyclic quadrilateral, even though this is almost impossible to find out the point, right? But this is the definition. Second, if I give you quadrilateral, so this quadrilateral, I can make sure the opposite 2 angles, they are complementary. Then automatically you can say this is actually a cyclic quadrilateral. Number 3, I should give you a number. This is number 1. Number 2, these are exactly the reversed theorem from the left. Number 3, if I give you a quadrilateral, so I can make sure there are 2 angles facing the same chord and they are the same. Okay, you will be able to determine this is actually a cyclic quadrilateral, which is exactly the same thing for the left. Number 4, if you can find out the 2 diagonals of this quadrilateral are breaking into 2 parts and they are, make sure the product of 2 from the one diagonal, they are the same as the other pair, this is also good enough for you to determine this is actually a cyclic quadrilateral. Same thing, if you can make an extension for the 2 sides, provided they're not parallel, and you can meet at one point, and then you can find out a relationship like here, PA, PC equals to PB, PD, then of course, you can also determine this is actually a cyclic quadrilateral. Last, if you can find out a relationship for these 2 diagonals and the 4 sizes, they are facing exactly the same condition. Again, you can also say this is actually a cyclic quadrilateral. So long story short, all the properties of a cyclic quadrilateral can be used as a determination rule to determine, okay, this is actually a cyclic quadrilateral. So there are actually necessary and sufficient conditions. Everything I write on the left is actually necessary and sufficient to the right. So that is actually, I think it's a very important property from the quadrilaterals perspective. It's a cyclic, or this is actually something vice versa. So far, so good? Yeah, I think this is pretty much what I want to say, talking about the basic properties. We're not talking about some flowery properties, which I will leave to the later like the later lectures, but these are the basic theorems that you guys is going to see from time to time. All right, with all those technologies, let's have a look at some real problems. Let's have a look at to see how we're going to solve the real problems using all the technologies we just introduced. All right, so far so good? Oh, good. Let's go to the second part of our lecture. We're talking about problems. Okay, let's have a look at how we're going to use the technology to solve some real problems. First thing first, let's go to our problem number 1. The first problem we're looking at is a problem that comes from 2018 AMC 12B, question number 25. Okay, the last problem from AMC 12B. Let's have a look how we're going to use the technology to solve this problem. So the problem says you have a circle omega 1, omega 2, and omega 3. They each have a radius 4. Okay, you can highlight this information. And they are placed in the plane so that the circles externally tangent to the other 2. So basically, you can say this is quite understandable. Points P1, P2, and P3 lies on omega 1, 2, 3, respectively. And P1, P2 is equal to P2, P3, which is equal to P3, P1. So essentially, you are creating what? This is a equilateral triangle, right? Okay, so far so good. All those conditions are actually very symmetric. Good, let's continue. And the line PI plus 1 is tangent to omega I for each I equals to 1, 2, 3, where P4 equals to P1. This is a little bit vague sentence. However, this is not telling something too flowery, just something like that. P1, P2 is actually tangent to omega 1. P2, P3 is actually tangent to omega 2. And then P3, P1 is actually omega 3. This is quite understandable. Okay, so see the figure below. The area of triangle P1, P2, P3 can be written in such a form: under root A plus under root B for positive integers, and what is the value for A plus B? Like I keep saying, this is a typical way how AMC like you to do the work, because AMC is like multiple choice, right? So they just, instead of asking you a big number, they always want to kind of change them into like whole numbers and then adding them together or multiple them together. So that being said, you have no way to guess. And also applies for Amy, because Amy is going to be like a positive integer for the right answer. So they always do a little bit trick like this. But generally speaking, the question is ask you to determine what is the area for P1, P2, P3. Okay. A question like this, how are we going to think? Well, the thinking process is always very important. Okay, so you have 3 circles, and they're kind of like externally tangent to each other. And you have like 3 lines. They're totally tangent to one to another circle, so on and so forth. And then the only condition the question gave you is, okay, the radius of the 3 circles, they're actually the same, which is 4. And the question asks you to determine what is the area. To determine the area of an equilateral triangle, I think as a conditional react, you need to find out, as long as I can determine P1, P2, the side lengths of a equilateral triangle, I should be able to determine the area of this equilateral triangle using the very famous condition, right? S of an equilateral triangle equals to under root 3 over 4 a squared. A is the side, right? These are all conditional react. You should have it right away. Okay, so that being said, $1 million question for our problem is trying to determine what is the side length of this triangle P1, P2, P3. Okay, so let us try to determine P1, P2. Okay, how to determine P1, P2? That's kind of like $1 million question for all of us. So before we jump to a solution, I think the most important thing is the thinking process. As long as you see such a problem, how do you think in order to solve it out? Right? That's $1 million question for everyone. If you guys can remember what I mentioned previously, as long as you see tangent and a circle, what is our conditional react? Do you still remember? As long as you see a tangent and a circle, how to make some auxiliary line, how to just try to make your life easy. If you can recall, let's go back. Let's go back. I mentioned here 2 things you need to remember. Either draw a line between the circle center to the tangent points, or connect 2 circles, like 2 circle centers, right? Then automatically you might have something. Trust me, if you use this, it's going to be so easy for you to solve the problem. Okay, in our problem, let's have a look. This is exactly our condition. We have circles And you have centers of like the center doesn't mention it here, but you of course you have centers. And as long as you have center, you make a connection. This is one thing. Second, as long as you have different circles tangent to each other, you should do a connection for the circle centers, and you will be able to solve the problem. Is that right? Trust me, you need to follow your heart. All those conditional react you remember previously should basically pay off for all your math competition. All right, so let's check it out. How are you going to solve this problem using this? I'm just going to erase this to save some time. I mean, to save some space. Okay, since this is like a quite symmetric shape, right? So as long as you do all your magic at one circle, I think this is going to be transferable to the other circle, right? So without a loss of generality, maybe I'm just going to find a center here, do a connection. This is going to be what? 90 degrees. And I'm going to find maybe another center here. Oops. I'm going to find another center here, do a connection. This is going to be 90 degrees, right? This is quite understandable. Okay, but after I have this, I know this is going to be 2. This is going to be 2, right? But it looks like they're not really talking to each other. One is in the omega 2 circle. The other one is like in the omega 1 circle. They're not talking to each other. How can I solve the problem? If you want to solve the problem, you need to make all the segments they're talking to each other. They can, build out some relationship. And taking from there, you'll be able to either create an, I don't know, like an equation or sometimes even an inequality, but taking from there, you solve the problem. But if they are just in the middle of nowhere, how can you talk, right? So intuitively, this is the thinking process. So intuitively, you want to make the connection between maybe these 2 red lines you just created, and taking from there, you might be able to do your work. Is that right? How to make sure they can talk to each other? I think the most straightforward way is doing some extension. Let them to, just force them to interaction with each other. I'm going to make an extension. I'm going to make an extension all the way to here. Let me just give a name. Maybe this is A, maybe this is B, maybe this is C. Okay, I think this is quite understandable, right? We're not doing any magic. Okay, so let's have a look at it. As long as you have all those informations in place, maybe you could be able to do your work. Let's check it out. Now I have this. First of all, I think, do you guys figure out this angle A? This is like a random angle, or you can use some condition to determine the length of this angle, like the measurement of this angle. Who can tell me? Can you figure out what is the measurement for this angle A? Is this just like a random angle, or it can be a little bit special? 60 degrees, is that right? This is quite understandable. Why? Think about it. If you don't understand why it is 60 degrees, you can check it out from here. P1, P2. Okay. BP1 is perpendicular to P1, P2, right? P3, P2. AP2 is perpendicular to P3, P2. Because P1, P2, P3, P2, they're actually what? 60 degrees, talking about the angle. So therefore, those 2 perpendicular lines, A, P2 and B, P1, they should also respect the 60 degrees. I think this is quite understandable, right? 60 degrees. Okay. And this is what? 90 degrees. Don't forget, right? Like I said, as long as you do the connection, you're going to have 90 degrees right away. Okay, now you're looking at what? A specific right triangle which contains 60 degrees, 30 degrees. Then automatically, you should know, let's say this is X. We're going to let AP1 equals to X. This is X. This is going to be what? Under root 3X, right? and BP2, P1, P2, under root 3x. Then AP2, 2x. 2x. This is our conditional react, right? So talking about this red triangle, it actually brings us a very important condition. All the x under root 3x, 2x, they're there. Okay. So it looks like as long as I can solve my value for a P1, let's say x, I should be able, you see, as long as I know x, I should be able to determine P1, P2. P1, P2 is under root 3x. And taking from there, I should be able to determine my entire area, right? So the $1 million question becomes, how can I do my x? Okay, in order to do my x, of course, I cannot do x just randomly in a vacuum. I should put x in a triangle, right? Hopefully, I can create an equation and taking from there, solve my problem. But it looks like the red triangle already finished its work. It contributes all those under root 3, 1, 2 relationship. I'm not going to be able to dig up too much for this red triangle. In order to create an equation, I must find out another triangle, right? So the red triangle is already done. It's already good to retire. I'm going to find another triangle. From the second triangle, I might be able to construct something, blah, 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 and then get what I need. So the second $1 million question is, how can I find out the second triangle? So these are the thinking process, okay? I can read you the question, I can read you the answer fairly quick, but let's try to focus on the thinking process. Now we're all good. X is the key. As long as we get a key, like I got a problem. But I need to find out where to solve X. To solve X, X cannot be randomly solved there. I must find out a triangle in order to help me solve X. So the $1 million question is, how can I find out the triangle? Okay, if you want to find out the triangle, I think the triangle won't be able to come from nowhere. It must come from the thinking process. We need to go back to our original thought. I said, as long as you have circle, you have tangent, you have two conditional react, right? The first conditional react is doing the center and the tangent point, which is already done. We still have a second conditional react. What is that? Connect the circle centers, right? Which we didn't use yet. You know what? All those conditional react, it does not come from nowhere. There must be some reasoning. You use the first one, it looks like you're going to use the second one as well. So how to connect the circle centers? Yeah, you already have two circle centers to create by yourself, B and C. So why don't you just do a connection for B and C? As long as you do a connection for B and C, congratulations. You should be able to solve this problem in this blue triangle. See, all the concepts are harmonic, right? Why you are doing connection? Because you have to do the connection from time to time. In this triangle, BAC, I'm just going to drag it here. This is B, this is C, this is A. Let's check it out, what we can do. This is 60 degrees. A, B, this is 2 plus X, right? X is your whatever you just mentioned. BP1 is actually the radius. And what about BC? BC is actually the distance between these two circle center. This is going to be 4 plus 4. 4 plus 4. Then what about AC? AC is actually here. Check it out. AC is here. This is going to be what? 2x minus 2, right? Because AP2 is 2x. 2x minus 2. Now you're kind of having a triangle You know the three sizes, sort of know the three sizes using x and some values, right? And also you know this is 60 degrees. Then who can tell me what should I do next? Who can tell me what should I do next? Your goal is trying to construct an equation, right? And taking from there, you'll be able to solve the problem. How can you create the, yes, I see somebody has the answer right away. Cosine law, right? You have this triangle, you have angle equals to 60 degrees. Just try to use the cosine law. Cosine law, that will be what? 8 square equals to x plus 4 square plus 2x minus 4 square minus 2, x plus 4, 2x minus 4, 1 over 2. And you will be able to determine the x value, 6/2 under 21, 3, which is pretty nasty, but consider this is the last problem for AMC. You're gonna do some calculation, right? This is so easy. And to solve this equation, you'll be able to determine the value for x. As long as you get x, you'll be able to get P1, P2, which is, I'm just going to give you the answer. It's pretty nasty answer. And then as long as you know the P1, P2, you will be able to determine the area, which is under root 2, 300, under root 252. That's it. You see, the thinking process is extremely important. Why you want to do that? Why you want to do the connection? You're not doing the connection for some random reason. It's because you're guided by the conditional react we introduced in the lecture. As long as you know this, you see, it's like fairly straightforward for you to solve this AMC last problem. So far, so good? Okay, if all good, let's go to our second problem. They're all using the conditional react we introduced in our lecture, and you're gonna find out fairly quick. Second problem, we're looking at a problem that comes from 2011 AMY 2 question number 10. Okay, the question says you have a circle with a center O and has a radius 25. Okay, so already give the radius. A chord AB of length 30 and a chord CD of length 14 intersect at a point P. Okay, you basically have two chords intersecting each other. The distance between the midpoints of the two chords is 12. Okay, and the quality, like the quantity OP squared can be written as m over n, where m and n are relative prime numbers. Find a number for m plus n divided by 1000. Like I said so many times, this is nothing but just try to facilitate the AMY's requirements. They want to generate a whole number from 0 to 999. So therefore, they're going to do something like this. But long story short, we need to find out what is the value for OP, or say OP squared. Okay, we're all on the same page. So let's check it out. How are you going to do such a problem? Have a good graph. That is actually the foundation for all the geometry problems. And I'm going to have two chords. Maybe one is AB. The other one, I don't know, it's maybe CD like here, right? So this is A, this is B, this is C, this is D. And you want to find the two midpoints. One is maybe from here. The other one is from here. Okay, you give it two names. This is E, this is F. Intersection, I give it P. Okay, so the question says R equals to 25. Okay, nothing to say. AB is equal to 30 and CD equals to 14. To midpoint EF, EF is equal to 12. With all those information, the question asks you to determine what's the value for OP. OP. How am I going to do for such a problem? Again, the thinking process is very important. So as long as you see such a problem, this is also a conditional react I want you guys to remember. As long as the question gives you a chord, let's say you have a circle, the question gives you a chord. I think automatically you should be able to determine what's the distance from the center of the circle to the chord. I think that one is quite easy. Why? Because this is going to be R. This is going to be your half of the chord. Let's say A over 2. Then using the Pythagorean theorem, you should be able to determine the distance from the circle center all the way to the chord. I think this is quite understandable, right? Nothing will, again, like nobody will against it. It's just basically using the Pythagorean theorem. So trust me, this is like so easy, but this will be considered as a conditional react. Conditional react. What is that? As long as you have the chord length, you should be able to determine the distance from the O all the way to the chord. You might use it, you might not use it, but it doesn't hurt. Just give it this conditional react and figure out what it is. Okay, so if that's the case, let me just follow what we just said. We're gonna basically do a connection. Do you still remember we mentioned as long as you want to make the connection from the mid of the chord, that is going to be perpendicular to the chord itself. Is that right? So this is going to be 90 degrees. This is going to be 90 degrees. And you can calculate this is 20, this is 24. These are so easy. I don't think we need to really calculate it, right? This is like so easy. OE is to 20, OF is to 24. And the question give you what? Another condition you didn't use yet. Another condition is 12. The distance between the two mid of the chord is 12. Okay. And with all those information, the question asks you to determine the length of OP. This is a little bit strange. It looks like I have already find a triangle. The triangle is here. So this triangle, I already know the three sizes, all good. But the question asked me to determine OP. Is there any kind of easy ways for me to determine OP? This is $1 million question. And why this problem goes to Amy, it really asks you to think about it from this way. Now I have a triangle OEF. I know the three sizes, but I need to determine OP. OP is not even within my triangle, right? But I might be able to use some flowery properties from this triangle and determine this OP. If you check the AOPS, this problem has multiple solutions, but the solution, what I will be talking about is the most beautiful solution. Just like Kai mentioned, why and how do you determine OP? Let's check it out. If I expand our vision like a little bit, not only to this specific triangle OEF, I'm going to put it into something bigger, into this quadrilateral. Trust me, I'm doing this for a reason. Think about it. My quadrilateral PEOF, this is going to be what? This is going to be a cyclic quadrilateral. Is that right? Because the cyclic quadrilateral, why? Because this is 90 degrees. Check it out. This is 90 degrees, this is 90 degrees. Of course, the opposite two angles, they are complementary to each other, right? And this is going to be a cyclic quadrilateral. Okay, as long as you know a cyclic quadrilateral, think about, we're talking about such a thing. First of all, cyclic quadrilateral means I would be able to make a circle. Let me change a different color. Right? Okay. So how can I use this to determine OP fairly quick? I think Kai mentioned using the Ptolemy. We actually have something a lot more faster without using Ptolemy. try to think about it. We actually talk about another thing. If I have a circle, I have an inscribed circle, I have an inscribed triangle, A, B, C. Previously, I mentioned something like this. The area of my triangle can be written as ABC over 4R, right? Do you still remember? ABC over 4R. And ABC have no problem, right? You can basically do it. But what about this 4R? 4R, R is the radius of this circumcircle. And AKA, it means what? OP equals to 2R. Is it right? OP. Why? Because this is 90 degrees. So the center of the circle must be on OP. So OP actually equals to 2R. So that being said, as long as I can determine 2R, I will be able to determine OP fairly quick, right? And how can I determine R? The question is already giving you. This triangle, this is the red triangle, right? Let me use the same color. This is my red triangle here. My red triangle is the triangle inscribed in the circle. So I should be able to determine S equals to ABC over 4R. ABC is already given to you, 20, 24, 12. S, you can use the Heron's formula, right? Heron's formula, you already know the three sides. It's so easy for you to determine the area. As long as you use the Heron's formula, you will be able to determine the area of triangle OEF. I'm just going to put it here. The area of triangle OEF, right, using the Heron's formula, will be equals to ABC, 20, 24, 12, over 4R. And you will be able to determine the value for R, right? As long as you determine that value for R, you will be able to determine the value for OP, which is 2R. Is that right? That is actually, I think, the best way to solve this problem without going to Ptolemy and the other random things. Of course, you can do that, but I think this is actually something quite understandable. You figure it out. So far, so good? Okay, so this is actually, again, a lot of conditional react we mentioned. As long as you see a shape like this, remember this is what? A cyclic quadrilateral. As long as you see a triangle, like a triangle inscribed in a circle, think about what we mentioned here. As long as you put all the jigsaws together, you should be able to solve the problem fairly quick. So far, so good? Okay, if all good, let's continue to another problem. Okay? The next problem we're looking at is a problem that comes from COMC. It's a 2012 COMC, question number 11. Question number 11. I think this is the last, it's the second problem from the last. It's the C part question. Yeah, it's the C part. Okay, we actually talk about this problem in our Euclid bootcamp, but we only talk about question number 1, question number B. But now let's go to question number C as well. Okay, let's get started. The problem says you have ABCD as a parallelogram, and we draw the diagram like the diagonal AC, and a circle is basically drawn inside triangle ABC, tangent to all the three sizes, blah, blah, blah. First thing first, the question asks you to determine DA plus AP equals to, let me change a different color to blue, DC plus CP. Okay, this is your first problem. Your second problem is basically you draw another line within the triangle ACD and make another 2 small circles tangent to all of the three sizes, right? And you want to give a let's say this is R1, this is R2. Just give two denotations for this two inscribed circle. And you want to prove that R1 over R2 equals to AP over PC. Okay. The third problem is that suppose dA plus DC equals to 3AC and dA equals to dP. And you want to determine the value for R1 over R2. Three problems. Like we keep mentioning from day one, for all the Canadian exams, the three problem, there must be progressive. So number one, it should be easy. Use whatever you got for number one to solve number two, and then whatever you got from number one and number two to solve number three. So this is actually a progressive. Okay, the Canadian exam are very nice, gentil, right? So it won't be give you a lot of like directly jump to the last problem. They will give a little bit hint gradually by gradually. Okay, so let's jump to it. How are we going to solve the first problem? First problem should be easy. dA plus AP equals to DC plus CP. Let's get started. What is dA plus AP, right? Let's change to color. dA plus AP. dA plus AP. Maybe I'm just going to give a name to X. This is X. This is Y. Because the question doesn't give you something too flowery. The only thing you can do is, let's say you have a tangent. Do you still remember from a point outside a circle, you make two tangents. So these two tangents should be the same in measurement. I think that's the only thing we learned so far. For this question, there's nothing too flowery. Let's get started, especially for the A part. Let's do some easy peasy stuff. And then taking from there, we might be able to get some inspirations, sparklings, so on and so forth. dA plus AP. dA, I don't think I can do too much. AP is actually equals to AX, which is quite understandable, right? AX. And what about DC plus CP? DC, I don't think I can do too much. CP can be written as CY, right? Because CP is the same as DY, the two segments. Okay, that's pretty much what I can do so far, right? There's nothing too flowery for this two, you see, there's like two tangents, that's it. There's another condition we should kind of think about it is actually what? ABCD is a parallelogram. Parallelogram means the two opposite sides, they're actually parallel and same in measurement, right? So that being said, I'm just going to do something fairly quick. dA, I won't do too much. What about AX? AX can be considered as AB minus XB, which is quite understandable, right? AB minus XB. Then DC, I cannot do too much. What about CY? CY can be considered as BC minus BY. These are quite understandable, nothing flowery. Now let's check it out, what we have so far. dA is actually equals to BC, right? So let's use the color. Two greens are the same because they are the two opposite sides of the parallelogram. AB is actually equals to CD. Again, two opposite sides of the parallelogram. Then what about XB and BY? XB and BY, they are again the two tangents from a point outside a circle, and they're also equal to each other. So AKA, the upper one and the lower one, they have the three color, right? Green, red, brown. So therefore, they are the same. QED. So easy. Question number one, there's always easy, right? Let's go to, I think there's nothing to say. Let's go to question number two. Question number two is that you basically draw the line AP and you make two inscribed circles squeezing there, and then you want to determine what is the radius ratio of this two inscribed circle. Okay, if I drag out the second problem will be here, right? have a radius here, have a radius here. This is R1, this is R2. Okay. Let's think about it. In our previous lecture, in our previous old summaries concepts, do you see something similar? Something familiar for you guys? At a certain point, did we talk something about the radius of the inscribed circle? Have we talked about anything about the radius of the inscribed circle? Check our notes. Everything we talked about previously, they are important for the entire math competitions. We actually talk about something. Still remember? As long as we have inscribed the circle for the radius, yes, the area will be R times P. Is that right? P is the half of the perimeter. So that being said, you see all those conditional reactors must be there for a reason. You see something like this, why don't you just directly plug in the formula? R1 over R2 equals 2. So R equals to what? S over P, right? S1 over P1, S2 over P2. Let's continue. S1, S2, P2, P1. Okay, I have to stop here, right? So that's all my magic. So let's go back to see how are we going to deal with S1 over S2? How are we going to deal with PR and like P2 over P1, right? This is P1. Let's go back to here. First thing first, how to deal with S1 over S2? 1 is here, right? Let me use the color. 1, let's try to use red. My red triangle is my number 1 triangle. My blue triangle is my number 2 triangle. First thing first, S1 over S2. 2 triangles, they're what? They are sharing the same height. So the area ratio will be the bottom ratio, right? Height is here. Where's height? Oops, let's change the color to here. This is the height, right? So the bottom ratio will be the area ratio. So it's going to be AP over PC. AP over PC. Let's go to the second one, P2 over P1. P2 is what? P2 is the half of the perimeter. P2 is also like the half of the perimeter. So perimeter 1 for, let me put it here. So for triangle red, perimeter 1, P1 will be half of AD plus AP plus DP, right? Divided by 2. P2 will be DC plus CP plus DP divided by 2, right? There's no magic. You want to make sure you want to do a division, P1 over P2 or P2 over P1. Check it out. Like I said, always don't forget what you already proved for question number 1, because this will be transferable to question number 2. Question number 1, you have DA plus AP equals to DC plus CP. DA plus AP, DC plus B, they are equal. And DP and DP, they are the shared side. So AKA, P1 is actually equal to P2. Is that right? These 2 triangles, they're actually share the same parameter. So therefore, this one equals to 1. Voila. R1 over R2 will be AP over PC. That is exactly what the question is asking for you. So easy, right? Like I said, let's do a quick recap. In this problem, we use here, inscribed circle, area is R times P. In the last AMY problem, we use this. Circumcircle area is ABC over 4R. So that's the reason why I say these two parts are so important. You might not realize the importance at one shot, but as long as you see all the problems connected, you will find out these two concepts will be used from Canadian exam to American exam, so on and so forth. They are so important. So far, so good? That's the second one. You see, every single step is not because you have the correct answer. Let's read the correct answer. You need to actually challenge yourself. How can I think it out by yourself? And the $1 million question for our entire lecture is talking about the thinking process. All right? Okay, let's go to our last problem. Our last problem might be a little bit challenging, but again, the thinking process are exactly the same. Let me drag the picture one more time, okay? Because we have already read a lot for question 1 or 2. Okay, let's drag to the third problem. The third problem says, suppose dA plus dC equals to 3 times of AC. Let's put it here. Where's dA? dA is here. DC is here. 3 times of AC is pretty weird. Why they want to give something like this? Okay, let's bear with it. And AD equals to DP. AD is here. DP is here. Okay, with all those information, again, the question asks you to determine R1 over R2. Okay, first thing first, R1 over R2 equals to AP over PC, right? Don't forget this, right? AP over PC. So that being said, as long as I can determine the value for AP and PC and taking from there, I might be able to solve the problem right away, right? Okay, so how to do this? Since the question, it looks like all the magic just focus on this, like this red triangle with these 2 blue lines, maybe I'm just gonna do my work there, right? So I'm just gonna let AP equals to X, PC equals to Y, because that's pretty much all the matching I want to do here. This is X, this is Y, okay? Then the question says AD plus DC equals 3 times of AC, of course, 3 times X plus Y, right? Okay. Also, so AD plus DC equals 3 times X plus Y. Also, I have to basically use some other conditions I did before. Like I said, for all the problems, for question number 1, you're going to use for number 2. Number 1 plus number 2, really, you're going to reuse them in number 3. So it looks like I have already used the condition from number 2. Did I use the condition for the number 1 as well? I don't think so. I think I can reuse it here. AD plus AP equals to DC plus PC, right? This part, AD, I don't really know. AP is X. DC, I don't know. PC is Y. Let's check it out. I have one question. I have one equation. I have 2 equations, right? These 2 equations have basically 2 variables. One is AD, one is DC, right? XY, I can take it as parameter. So that being said, I should be able to find out AD is X plus 2Y. DC is 2X plus Y. So AD is X plus 2Y. And what about DC? I'm going to erase this. DC is actually equals to X, 2X plus Y. Okay, 2X plus Y. Now you are kind of dueling your thing into such a triangle, ADC. You already know this is X plus 2Y. This is 2X plus Y. This is Y. This is X. Okay. Is there any other condition you didn't use yet? Is there any other condition you didn't use yet? Let's check out a problem. The problem says you have dA plus DC equals to 3AB, and dA equals to dP. Oh, the 2 blue lines, they're actually what? they're equal to each other, aka this is like an isosceles triangle. As long as you know an isosceles triangle, it looks like for this problem, you have nothing to do but deal with all the sides. So what kind of thing you can get from isosceles triangle? Taking from here. Who can tell me? If all the way you come to here, you are facing the problem, right? You basically have an idea. This problem is going to deal with later when you're going to create equations, you're going to deal with all the size, right? I don't think you're going to take too much about angles. Let's deal with the size. And all of a sudden, the question gives you a isosceles triangle. What are you going to do? Yeah, I see many students has the correct answer. Isosceles triangle, you want to use all the size related stuff to basically do the work. Forget about the angles because like I said, looks like this problem is just gonna play around with the size. Forget about all the angles. The most efficient way from an isosceles triangle is doing what? Let me change color green. Is doing a connection, making a what is called perpendicular line. The perpendicular line will gonna be the midline for like the median of the bottom. So this is going to be x over 2, and you get a 90 degree for free, right? You get a 90 degree for free. Let's say give a name M. So far so good? Because having a perpendicular line as the medium, that's actually the most low cost way, most straightforward way to use this side relationship from isosceles triangle. If you want to do something more flowery, then you might use the angles. But like I said, it looks like this for the entire problem does not talk anything about angle. Maybe we need to focus our discussion for the size. So these are the thinking process, extremely important thinking process. Okay, now voila, maybe I'm just gonna do my work, basically use whatever I have it here. How can I do my work? Later, moving forward, I'm probably gonna find out an equation. Find out the equation, I'm gonna find out relationship between x and y, and taking from there, I'll be able to solve my work. The $1 million question is, how can I find out the last equation? Who can tell me? Maybe we can ask Rochen to give us some ideas.
Okay, so I think we can use like the Pythagorean theorem twice to construct two equations. Like the first one is in triangle ADM.
Yep.
Then we have 2x, x over 2 squared plus actually x plus 2y squared minus x over 2 squared is equal to this, like this dm. And this is also equal to, in the other triangle, 2x plus y squared minus x over 2 plus y squared.
That is correct. Yes. And taking from here, this is going to be a very important conditional react. You don't even have to think about it because this technology was tested millions of times in the AMC. That's the famous double Pythagorean theorem. I'm just going to rewrite it here. Oops, maybe something like here, right? 90 degrees. As long as in the problem, you see two triangles, they are sharing the same height. Your first conditional react, I think we talk about so many times in our AMC bootcamp, is actually the double Pythagorean theorem. Do not even think about anything else. That's the only thing, the most straightforward solution for all those problems. Two triangles sharing same height, double Pythagorean. So in our case, I'm just gonna write it right here. You're gonna have what? AD square minus AM square equals to dm square. This is for this red triangle. And continue for this black triangle, you're going to do exactly the same thing. Right? This is going to be dc square minus cm square. Cm square. Is that right? Just plug in the value. X plus 2y square minus am is x over 2 square, because the perpendicular line for isosceles is also going to be medium. dc is 2x plus y square minus cm. Cm was what? Cm is y plus x over 2 square. Right? So easy, huh? So this way, do some quick simplification. You're going to have 3x minus 4y. Our lecture never focuses on the calculation, so we're just going to give you the answer. So for sure, this one can be ignored. X over y equals to 4 over 3, right? X over y equals 4 over 3. But the question doesn't really ask you xy, right? The question asks you the value for R1 over R2. However, we just mentioned R1 over R2 equals to AP over PC, which is x equals to y, 4 over 3. Is that right? You see, this Canadian problem, this is pretty much the last geometry problem for us, for our COMC. And this problem is also the last from the, I think the second from the last of that year. But generally speaking, as long as you follow all our technologies, you should be able to solve the problem so quick, right? Nothing too flowery, too complicated, and you're good to go. So far, so good. Just try to remember, like the $1 million question is the thinking process. How do you think? You cannot randomly jump to here, jump to there. This problem, every single step, you need to guide it by your conditional react. And we have 8 sessions in total, right? Our entire 8 sessions is talking about all those conditional react. If you all have all those 8 sessions while you go to our boot camp, why every single problem is so easy? Because they just follow our conditional react, and it's good to go. So far, so good. Okay, if we're good, let's go to the last problem of today's lecture. I'm going to give you a Chinese MO problem. This is a 2014. It's a Chinese Math Olympia. Winter camp problem, but it's the same complexity, I think. So this problem says like this, because we don't really have the English version. I'll write it here. Let A, B are 2 fixed points. Angle ACB equals to alpha. Alpha is between 0 to 180. Triangle ABC inscribed in circle I, and the tangent points of the 3 sizes are F, E, D. EF, AI, BI intersect at points MN. Try to prove the circumcircle of triangle DMN passes a fixed point. I'll let you guys finish the writing, and then I'll give you the graph. Let AB are 2 fixed points. ACB equals to alpha. Alpha is from 0 to 180. Triangle ABC is inscribed in circle I, and the 3 tangent points of the 3 sizes are ADF. Later, I'll show you. Yes, it's a Chinese M, no, not Chinese USA MO, Chinese MO. And EF, AI, BI, they intersect at the 2 points M and N. Basically, the question asks you to prove the circumcircle of triangle DMN passes a fixed point. Yeah, it's the Chinese equivalent of the USA MO, yes. But this is actually a relatively easy problem, so I didn't really make it super complicated. Later, with our courses moving through, we're going to see more and more complicated problem. This is only our first lecture. It's considered to be introductory problem. Okay, with this, I'm going to give you the graph. Okay, I'm going to put here's this circle. So basically, you have a inscribed, like a circle is inscribed here. And you have these 2 points here. And this is the tangent points. Yes. I'm just going to M and N. Okay, EF. Okay, M and N is here. ACB. I'm just going to give you this graph here. It's here. This is here. This is here. Here. Okay. Have A, B, C, E, F. This is I. This is N. This is M. This is D. Okay. So let me just repeat the problem one more time. The question says AB are 2 fixed points. C is also another point. And ACB, this guy equals to alpha. Okay? This one equals to alpha. Alpha is between 0 all the way to 180 degrees. Triangle ABC, it basically has an inscribed circle, right? This inscribed circle, I is here. Maybe my graph is not so good, but basically this is kind of like I should be the center of my inscribed circle EDF. Okay, so basically this inscribed circle is going to tangent with my 3 sizes at EDF, 3 points, right? Okay, and also you want to make a connection for AI and then make it connect all the way to M, make a connection to DN and make it all the way to connect and extend it to N, right? With all those information, the question says, please determine the circumcircle of triangle DMN. Let me use the color. The circumcircle of this DMN triangle will pass a fixed point. So this problem is a little bit challenging because you don't even know what this fixed point is. Is that right? Because the question doesn't really give you the fixed point. So your first $1 million question is, which point is the fixed point? Is that right? It's quite understandable. So this is also a very important conditional react. If the question does not really give you a point, you need to find out the point. Apparently for this problem, you need to find out the point, right? So I think this point cannot be so flowery. This point cannot be a very weird point or something like here, right? Because how come you're so clever, so smart to guess what the author thought? The point must be very conspicuous. So when you want to do the guess, trust me, you must guess something very easy in order to make it work. If you guess out something so flowery, so complicated, there's no way for it to work. Is it right? Okay, and for this problem, I'll basically tell you upfront. the fixed point is actually here. The mid of AB. We find O as the mid of AB. Later, I'm going to use all the technology we introduced. Just try to find, okay, O is the fixed point for the entire DMN circumcircle. So let me ask you a question. So that being said means what? If I can translate the language a little bit, what I need to do in order to make sure O is a fixed point for the circumcircle of triangle DMN. Who can answer my question? Now we're on the same page. We need to prove D is the point. What point? The circumcircle of triangle DMN basically passing this point all the time. But this is more like a human language. Can I use a more mathematical language? What does it mean from a mathematical language perspective? What I need to prove? Who can tell me? Using all the technology we introduced today, you should be able to answer the question. Because now we're on the same page. We need to prove O is the fixed point that the circumcircle of triangle MDN must passing through. But that's not a, but this is something too like English, right? I don't think that this kind of English language can be proved, but we need to convert it into a more mathematical way. What's the mathematical way to translate this? Yes, DOMN, cyclic. I want to show, want to show DMNO cyclic, right? If they are cyclic and O is actually the midpoint of AB, O is actually fixed there, right? Because AB is fixed, O is fixed. So therefore, they're always passing through. Okay, so let's try to find out how to prove DMON cyclic. This is the thinking process, right? So let's check it out. For this angle, I'm gonna put it here. Maybe I'm just gonna make a screenshot for this because I'm gonna use this in the second graph. Sometimes for the geometry problem, you really have to come back and forth using check the graph from time to time. I'm gonna save it. And then I'm gonna go to the second page. I'm gonna use it. Okay, there you go. I'll put it here. Okay, let's check out angle CEF. Angle CEF, is there any special condition, special thing for angle CEF? Because as long as you do a tangent from outside the circle, you will always make sure these two sides are the same. Exactly what we introduced today, right? So therefore, angle CEF is actually 90 degrees minus C over 2. Is that right? You just make, because these two angles are the same, you're 180 minus C divided by 2. So CF equals to 90 degrees minus C. Okay. Also, let's check it out. Let's check it out. Angle CEF equals to this, then I is what? I is the incenter of the triangle. This is C. So you take it out from here. I, right? I is the incenter of triangle. This is A, this is B. Okay, who can tell me? If that's the case, is there anything special for angle C and angle AIB? Who can tell me, is there anything special for angle C and angle AIB? As long as you're talking about a in-center. Yes, because we see somebody has the correct answer. Because angle C plus A plus B equals to 180 degrees, right? Also, A plus B divided by 2 plus C equals to 180 degrees, right? Right? AI, oh, no. So, sorry. I mean, angle A plus angle B divided by 2 plus AIB equals to 180 degrees. This is AIB. This is half of angle A. This is half of angle B, because the in-center basically find out what is the relationship. So that being said, I would be able to find out what is the relationship for angle C and angle AIB. Is that right? Because angle C will be equals to, let me put it here, A plus B will equals to 180 degrees minus C. A plus 2 divided by 2 will be equals to, this is going to be 90 degrees C over 2. Is that right? 90 degrees C over 2. So that being said, 90 degrees C over 2 plus AIB equals to 180 degrees. So AKA angle AIB will equals to 90 degrees plus C divided by 2. Is that right? I think this is quite understandable for this entire, like the in-center related stuff. So that being said, I'm going to put it here. This one equals to like this, right? Because C can be replaced by using AIB minus 90 degrees. So far, so good? Okay, 180 degrees minus AIB. AIB is what? AIB is here. This is AIB, right? 100 degrees minus AIB equals to what? Equals to here, right? AIN. Is it right? AIN. Okay, so that being said means what? Angle CF is actually equals to angle AIN. Let's check it out. Let's check it out. CEF is here. AIN is here. If this guy equals to AIN, aka it means what? This guy plus this guy equals to 180 degrees. Is it right? Are we on the same page? Yes or no? So AEN plus AIN equals to 180 degrees. Yes or no? Can I have some feedback? Yes or no? Can I have some feedback? Are we all on the same page? Okay, perfect. If that's the case, it actually means what? E, N, I, A. They are cyclic, right? They're cyclic quadrilateral. Therefore, I, N, E, A, cyclic. INEA cyclic. On the same page, right? Also, we know IEAD cyclic. Let's check it out. Use different color. IEAD. They are cyclic. Why? Because if I make a connection for EI, E is what? E is the tangent point. This is 90 degrees. This is also 90 degrees. This is exactly what we mentioned, right? The 290 degrees, the opposite two angles, they're cyclic, right? So this is also cyclic. So that being said means what? I, N, E, A, D. These 5 points are cyclic. Are we all on the same page? If I use the color red, E, N, I, D, A, all those 5 points, they're cyclic. So far, so good? Okay. If they are cyclic, let's try to do the same thing. Same thing, you can prove B, F, M, I, D, cyclic. What is that? You finish the part on the left, then you should know everything applies on the right. B, F, M, I, D. These 5 points are also cyclic. Is that right? Are we all on the same page? Okay, let's continue. Why I'm doing this? Let's continue. Now, because AID equals to 90 degrees, I can say AI is the diameter. Let's check it out. Like ADI equals to 90 degrees, right? Now AID, ADI. ADI equals to 90 degrees. This is 90 degrees. You just tell me that, right? If ADI is 90 degrees, so that being said, my AI will be the diameter. AI will be the diameter of my radius, of my circle, right? So that being said, what? A and B. If this is the diameter, right? So A and B, A and B. Will be equal to AEI equal to 90 degrees, right? Because they're all facing the same AI, right? Because AI is the diameter, and you have seen 1, 2, 3, 4, 5, they're all cyclic. And they're actually facing AI as the same diameter. So therefore, this is 90 degrees. This is also 90 degrees. Is that right? Are we all on the same page? So A, N, B, and A, E, I, they're both 90 degrees. I'm just going to write it here. A and B equals to AEI equals to 90 degrees. Actually, the same thing applies on the blue part. A and B equals to FBI equals to 90 degrees because they're exactly the same. Everything I did for the red one will be the same for the blue one. Okay? So that being said, as long as you see this, you can find out M and N. They're both on the circle of AB as the diameter. Why? Because you can find out A and B equals to 90 degrees. Let's see. And what? And A and B, exactly the same thing. This is also equals to 90 degrees, right? So that being said, M and N, they will be on the same circle, and this circle using AB as the diameter. Are we all on the same page? Let's stop it for a sec. Yes or no? Because I find out this is 90 degrees. This is 90 degrees. They are all facing the same length AB. So therefore, MN must be on a circle using AB as the diameter. So far, so good? Okay, perfect. Let's continue. We have already constructed O, but I didn't use O yet. Let's try to use the O, right? I'm going to connect OM and ON. Okay, MON will be twice of MAN. Is it right? MON will be twice of MAN. Why? Because you just tell me that MNOB, this is cyclic. And MON is actually what? Our center circle, our center, like what is called center angle. And your MAN is the inscribed angle. We just said the central angle is actually twice of the inscribed circle, right? Of the inscribed angle. So I can actually say what? MON is twice of MAN. All good? This is for the red one, and exactly the same thing for the blue one. The other one is what? MBN, right? MON will be twice of MBN. If MON is twice MAN is twice MON, like MAN is twice MBN, it will be if I take one for each. Right? It's twice the first part, twice the second part. I take one of them, put it together. That is exactly what I need. And MAN plus MBN actually equals to NDI plus MDI. Why? Let's check it out. Let's check it out. Let's check it out. MAN is here. Let's use the green one. This is my MAN, right? MAN actually equals to NDI. NDI. Why? Because we just proved NIDA. They're cyclic. If you're facing the same chord, NI, of course, these two angles are the same. Same thing applies. Your MBI will be equals to what? Will be equals to MDI. Again, because I said MIDB, they are cyclic. So they are actually facing the same chord, NI. Is that right? So therefore, this is valid. But MDI plus NDI actually equals to MDN. MDN. What is MDN? MDN is here. Okay, voila. Now you prove that your MON, let's drag it out here. Your MON equals to this MDN. So that being said means what? If I use the brown, MNDO, they are cyclic. This is actually using one of the property we just introduced, the facing the same chord. So this is cyclic. So therefore, you can make sure the circumcircle of MDN will always pass O. So just one more line, we're good to go. Therefore, MNOD cyclic. Therefore, O is the fixed point. Voila. You see, this problem might be a little bit challenging. It's not as easy as our North American problems. But again, I'm not using anything flowery. Exactly the same strategy, the same way we keep talking about from day one in our lecture. So again, that being said, our entire lecture is trying to teach you guys all the technologies we introduced from day one, okay? And you'll be able to solve it out. So student got a question. I don't really get why CEF equals to AIN. That's the very beginning. Yeah, I can do that. CEF equals to 90 degrees minus C over 2, right? And I mentioned that because I is the inscribed circle's center, so therefore C plus AB equals to 180, and A plus B divided by 2 here and here plus AIB equals to 180. Why CEF is equal to 90 degrees minus C divided by 2? Oh, that one is easy. CEF is here. CEF is within this triangle, right? This is an isosceles triangle. Isosceles triangle means CEF equals to CFE. So CEF plus CFE plus C equals to 180 degrees. So CEF is 90 degrees minus C divided by 2. You got me, Kai? Okay, so hopefully that answers your question. Okay, so I think that being said, we actually finished our first lecture. Our first lecture focused on basic concepts for this circle. And we give you some problems, give you some technologies. Try to remember all those conditional react we've introduced from day one will be quite applicable for all those following problems. Okay, so that being said, that wraps up our first problem. And I'm going to give you some homework after our lecture. And in the next lecture, we're going to go to the second part. We're going to talk about power of point and some flowery problems, how to use power of a point. All right, that's pretty much for today's problem. You have any questions for me? All good? Perfect. If all good, I'll see you guys for the next time. All right, bye guys.